Hi everyone, thanks for attending this talk. My name is Prasann. Today I'll be talking about some joint work with Tanya, Goyal, Jiacheng, and Durrett at UT Austin. So I'd like to start this talk off with a story. Once upon a time, there was a child named Bob. Now Bob was a special child, and he used to love writing short and concise answers in school. So one day when he had to write an essay for his class, he decided to just submit a single sentence response. Now his teacher was obviously not a huge fan of this. Bob got in a lot of trouble, he failed the essay, and specifically the feedback his teacher gave him was, Bob, this is incorrect. Also, write more long essays. So Bob learned his lesson. He decided to start writing longer essays, and he went on to do much, much better in class. But there's one important thing that his teacher didn't realize. When he was giving his feedback, Bob didn't hear the whole thing. Bob just heard, write more long. This might come back to bite him. So Bob grows up. What kind of person does Bob become? Well, you know that one friend who always loves to respond to your text messages with these incredibly long mountains of text every single time? Bob becomes that friend. Bob becomes the kind of person who, instead of writing short announcements for his organization, writes short stories. And instead of giving his advisor quick experiment proposals, writes whole 50-page manuscripts instead. So what can we say about the story of Bob? Well, we know that longer and more informative responses oftentimes can be better, but that there are also lots of other axes of quality that we might want to improve on. So what does this mean for large language models? Well, just like Bob, we want to know what exactly are they learning, and does this align with maybe what we might expect? Now, in the case of Bob, however unfortunate it was, we do kind of know what was going on there. In the case of something like supervised fine-tuning, we also have a rough sense of what's going on, where the idea is there's some training data set, we want to maximize likelihood over that training data set with some model while fine-tuning it, and we get a new model that generally outputs stuff that looks like the training data. But what about something like reinforcement learning from human feedback, or RLHF? Well, in this case, we're working with newer, oftentimes weirder kinds of data, where it's not actually clear what's exactly getting learned here. This is what we wanted to investigate in this work. What exactly is RLHF learning? Now, to give some background on RLHF, it can be broken into two components. The idea is that we have some preference data that looks like this, where there's some question, some preferred response, and some dispreferred response, usually labeled by humans. And we want to get some sort of reward model or scoring model that basically gives higher scores to outputs that are preferred by humans and lower scores to outputs that are dispreferred by humans. The idea is that if we have this kind of reward model, we can then do some sort of policy optimization process, some fancy algorithm like PPO, to get a new RLHF model that has, on average, higher output reward. With the idea that if reward corresponds with human preferences, then humans should like this new model more. And indeed, at the time, people were finding that these approaches were leading to better models according to humans. So we decided to start running our own experiments. We wanted to understand where are these improvements coming from. So we did exactly that. We trained our own reward models, and we immediately started noticing some weird stuff. When we would plot reward model score against output length on sort of training data or other output data, we were finding these really strong and weird correlations between length and output reward. So immediately we were like, this is a little bit strange. Then we would look at actual RLHF and we'd do successful optimization. And again, we would notice this weird pattern where we'd start off with reasonable looking SFT models and then just get these way, way longer outputs after RLHF. Again, we were like, what's going on here? Is it possible that something maybe undesirable, just like in the case of Bob, is going on here? This brings us to our main hypothesis, which is that RLHF might primarily be making outputs longer and barely optimizing for other features. Given the increasing popularity of these algorithms, we thought that this was potentially very concerning and that's something that we need to look into more. In this talk, I'll be going through this exact hypothesis. I'll be talking you guys through 3 experiments that we did, validating this in different ways. This includes things like trying to quantify exactly how much length is accounting for optimization in these settings, and finding that length is accounting for quite a bit of optimization here. We do a length-only optimization and find that it's actually able to reproduce or be very comparable to full RLHF optimization pipelines. And at the end, we see if there's actually ways to fix it, given that we know that this is a problem. I'll be starting with this quantification experiment. Now, to give a brief overview of our task settings, we wanted to get a diverse and realistic set of task settings to test this hypothesis on. So we look at 3 preference data sets. One of them is this WebGPT preference data set, which is single-turn web QA data with human-labeled preferences. Another one's this RLCD data set, which involves multi-turn chat QA, where the way these preferences are gotten is you have some larger language model and you prompt it to get a good and a bad output. And then lastly, we have the stock preferences data set, which if you're familiar with Stack Overflow, basically just that, and the preferences here are based off upvotes. Okay, so let's make our hypothesis a little bit more specific. What exactly do RLHF models learn during post-training? Now, we already have that PPO is increasing length on our settings. This is an initial observation. We also know that reward models are strongly correlated with length on these settings. So given the fact that we know that PPO is supposed to increase this y-axis or lead to higher overall reward outputs, how exactly is PPO doing that? Now, one possibility is that PPO is learning off of a variety of features, in which case we expect something like this green sort of circle, where the new distribution should mean higher reward at all sort of different lengths. But then there's this more concerning hypothesis, which is that, maybe reward is only optimized via length, where we're seeing this distribution of length shift to the right, and that's where all of this reward improvement is coming from. So it's concerning because it might mean that nothing else is actually being learned here. So we test this. We do what we call a stratification experiment. I'll walk you guys through a visualization of this. The idea is that we start off with some largish prompt set, and then we generate a bunch of outputs with our SFT model, which I'll indicate with these black dots. So we get this, and here I'm grouping the outputs based off of common output length. So outputs that are in similar output length bins are going to go into sort of similar reward score bins. Then I look at the RLHF model, and we look at again, generating outputs on the same set, grouping them by length. Where do they sort of go? And immediately what you'll notice is that given the whole point of RLHF is to maximize this y-axis, it's kind of weird that these red dots on average don't actually seem to be that much higher than these black dots. Even more stark, when we compare this against the overall reward gain that we see from doing PPO training, we find that it's much, much less. And overall, we're finding that length is actually accounting for around 85% of reward improvement in this setting, suggesting that, going back to that initial question, there is evidence that indeed reward optimization could be attributable to shifting to longer outputs. And this is something that we find across our different settings. So that concludes that first experiment. Given this, there's some evidence that RLHF might be boiling down to some sort of pure length-based optimization. So an obvious way to maybe test this from the other side is to maybe just try doing exactly that. Let's do pure length-based optimization and see if it gets us similar models, according to popular evaluation. So we compare normal PPO to this length PPO approach, which is basically just optimizing for a target length where we set that length to be something comparable to the normal PPO approach. Given this, we also then have an SFT best of n based baseline that just controls for length biases and evaluation. Now, on these plots here, I have on the y-axis just simulated preferences, which if you're familiar with alpaca eval, this is an earlier version of that. And the idea is just higher is better here, over 50% particularly. And what we find across the board is that length PPO is actually giving comparable improvements to full RLHF. Again, giving us some evidence that indeed RLHF could be coming out to something very comparable to pure length-based optimization. So now that we have some evidence suggesting that length indeed is a problem here, and that we might want to fix it somehow. So we do exactly that. We see, is this actually possible to fix? So to do this, we go across the RLHF pipeline, trying a bunch of different interventions, countering length, and seeing if any of them actually work. We try things like rebalancing the length distribution, preference data, randomly augmenting preference data, doing some sort of truncation of easy examples based off of a train dynamics analysis, penalizing reward past some threshold length, rescaling reward based off of a moving average, omitting long outputs, and increasing our KL penalty. So a bunch of different things that we're trying here. I'm not going to get into the details of all of these, but just to give a flavor of what this looks like, this first one, so if there's a preference, if there's a bias in your preference data set where 55% of the time humans prefer longer outputs, we can simply balance that bias and then get new reward models, see what happens there. And likewise, directly on the reward model as we're doing PPO, we can set some sort of penalty where, if you go above 100 tokens, maybe just dock every single token by a little bit of reward every time you go above that threshold. So that's what this looks like. So in order to know whether an intervention is effective or not, we want to know two things. We want to know that firstly, according to those sort of simulated win rates or downstream evaluations that people like to use, that we're not actually seeing any decreases in performance compared to normal PPO. And here on these plots what I have is basically blue bars mean that there's no degradation compared to normal PPO, and red bars mean that there's a little bit of a drop as a result of doing this intervention. So already we see that a lot of these interventions are harming optimization a little bit, at least with respect to this evaluation. More importantly, though, we want to know that these interventions are actually effective in countering length. And what we find is pretty surprising. We find that length is actually still dominating in almost all of these cases, or leading to failed optimization. Specifically, 20 out of 21 of these preference pair intervention pairs are leading to issues, and we're still seeing length go up compared to the SFT model. So to conclude, we find in this talk that RLHF is optimizing for length to a degree I think a lot of people weren't expecting at the time. We find that pure length-based PPO is actually able to match normal PPO, and that this is quite hard to counterbalance, with many interventions not seeming to do the trick in terms of avoiding this behavior. It's worth noting here that length is not an inherently bad feature, but over-optimization of length at the cost of all other possible features is bad. Thankfully, there's been a lot of work since then looking into how to potentially fix this issue. We looked at PPO, but there's various other algorithms, for example DPO, where people have actually also noticed length over-optimization behavior and have been actively working on trying to fix it. Likewise, following that length-only PPO experiment, there's been a lot of increased interest in trying to build evaluation that's better equipped to control for length and potentially help us pick up on these kinds of shallow patterns without having to do this whole sort of thing. And lastly, I think a big takeaway is that we need better preference data and better reward models if we want to avoid this kind of thing. And likewise, there's been lots of steady progress in trying to get both of those. Now, this is all great, but it's worth noting here that length is only one simple feature out of a variety of possible simple features. It's still totally possible that there's 5 or 10 other shallow features that are still dominating in these settings that we're not aware of. So I'd ask you guys to keep an eye out for this and think about some of the analysis that we've done here today and how it might apply to your own research. And hopefully we can work towards having less and less of these issues as we work towards better modeling and evaluation. Either way, there's still a long way to go. Thanks, everyone.